reaction rate and temperature. So as the temperature increases, the reaction rate increases. And this is due to the molecules having enough of that energy they need to properly collide to break bonds and form new bonds. The Arrhenius equation is a very long calculation derivation that takes a little bit of time, a little bit of calculus to come to, definitely high-level math. And we're going to involve that here, and I'm just going to give you that instead of take the time to go through this. The ln of K2 over K1. So in this case, we have two rate constants. We have activation energy value given, and R, we'll talk about that, what that is in just a moment, and then two temperatures. So you're going to see a change in temperature and a change in rate constant within a reaction. So important to point out here that K2 is on top, but T1 comes first. It'd be very natural to put K1 over K2, but this is not the case. It's going to be K2 over K1, so K2 over K1, but we do have T1 and T2 in what would seem like a logical order. So we need to be able to convert all of our temperatures into Kelvin. To do that, we're going to do degrees Celsius plus 273.16. Remember, sig fig rules would say that however many decimal places is how many decimal places you have. Let me try that again. The smallest number of decimal places you have in your C and or this 273.16 would be the smallest number of decimal places you should have in your final answer. So K2 is the rate constant at T2, and K1 is the rate constant at T1. And then E sub A is the activation energy. R is this constant. We're going to be using it in this way mostly, 8.3145 times 10 to the negative third kilojoules per mole. And then T1 is temperature in Kelvin, and T2 is temperature in Kelvin also for the second temperature. So here is just a slide that repeats some of that information, giving you the formula and the R that we're going to use, and don't forget to convert into Kelvin. This will be given to you, and you do need to write it down in every problem that you use this with at the beginning before you even start. So this is worth points, just writing down the generic formula. Okay, so for 22A, it says for a certain reaction, the rate constant doubles when the temperature increases from 15 to 25 degrees Celsius. So rate constant doubling means we're just going to pick a rate. I'm going to make it very simple, random rate, because this doesn't give us a value. It just tells us it doubles. So we're going to put K1 as 1 and K2 as 2. I could have done 100 and 200. I could have done 50 and 100. Whatever I did, I just needed to double it. Wouldn't have mattered. I also know that my temperature is 15 to 25. I like to make my first my K1 or T1 and my second my K2 or T2. It really doesn't matter what you make 1 and 2, as long as whatever's occurring at the same moment, the T that goes with the K is 1 and the other T that goes with the other K is 2, or vice versa. So I converted both of these into Kelvin, and there should be a K on here. I'm leaving out some units here, being a little sloppy, so let's add the K's in here. And these would have been degrees Celsius here. So let's add that in because that's appropriate. And so because this had 0 places past the decimal and this has 2, 0 is smaller than 2, so that's why that's rounded to no places past the decimal, and likewise there. Brought my generic equation in. Now let's start plugging some things in. Okay, lots to look at here, but I'm going to take it in step by step. So I know that it would be best if I labeled things, which I already did in this way. You could have also labeled things up here. I'll show you that in the next example. I got my generic formula and need this to get points, to get full points. I'm going to put my K2 on top over my K1. And there's no units on here. I just know from the next part of the problem that I had it in seconds. E sub A, because we're solving for E sub A, I know my R. The R is something you're going to plug in every time. You don't have to think about that. It's going to be this value always. We'll use the kilojoules version of this. 1 over T1, my T1 was 188. Okay, 1 over T2, which is 298. I think I said 188. This was 288. 1 over 288, because my T1 is 288. 1 over 298, which is my T2. Okay, so the next line here, I took the ln of these numbers. So I plugged this into my calculator. I got 0.693. And I took here, this is still saying nothing there. Nothing is the same, nothing new there. I took 1 over 288 and did that. I took 1 over 298 and got this value. So the next thing I did here is just brought this down, and I subtracted these two values here. And now to solve for this, right, to get E sub A by itself, I need to get rid of this. So this is on the bottom, so I got to multiply both sides by this. So when I multiply 0.693 and this by itself, I get this number on the left, and then what's left would be e sub a times 1.1 to the negative fourth. Now to get e sub a by itself, I divide both sides by 1.10 times 10 to the negative fourth, inverse Kelvin. Kelvin goes away and cancels, and I have e sub a to be 52.4 kilojoules per mole. I encourage you to set this up, starting at this point right here. Work the math yourself and see if you can get my answers. If you have any questions about the math or the algebra, please do not hesitate to reach out.